Hello friends, welcome back to our channel. So today we'll see one more concept in algorithms, that is optimal binary search tree. Optimal binary search tree. So which can also be called as OBST, and this by using the dynamic programming. Okay, so we have to implement this one using dynamic programming. So we know that dynamic programming means the working of dynamic programming will be similar to the divide and conquer method. So where the complete problem will be divided into sub problems and that will be solved, and the solutions of each sub problem will be stored in a memory, right? So that we can implement by using a top down approach and the bottom up approach, and the process we call it as a memorization and the tabulation. So the same concept we are going to use in this particular OBST, optimal binary search tree, which is an application of dynamic programming. Now we will recall about the tree. So a tree is nothing but nodes and vertices. Okay, and coming to the binary search tree, so we have seen about the binary search, right? So the constraint of binary search is to maintain the sorted elements. That means we have to first the elements to be get sorted, and then only we have to apply the binary search tree. And here we will be having the root node in this binary search tree, and on the left hand side of this root node all the elements should be less than the root element, and on the right hand side of the root should be greater than the root elements. So if the tree satisfies this one, we can say it as a binary search tree. Okay, so for example, let us take some 10, 20 and 30. So you can consider 20 as a root, and left hand side the less than element, and right hand side it is a one more element, that means a greater than root. For example, the same thing, if you consider 30 as a root, left side you can have a 10, and on the right hand side of 10 it will be a 20. And you can see on the right part, right hand side of this root, we are having all the elements of which are less than root. And if you consider 10 as a root element and 20 is on the left hand side, sorry, right hand side, because greater than 20, and 30 is the right hand side of 20. And similarly, you can also go with a 30, with a 20, with a 10. See, all these are the different cases. So we can draw the binary search tree for these three elements in these multiple ways, right? Now the question is optimal. How we can say it as an optimal binary search tree? So the mainly binary search tree, the name itself indicates it is used to search the element in a tree. For example, if you want to search for 30, so it will be here, and it will be here, and it will be here, and it will be here. So for searching the element, we will be using this binary search tree. Now what about this optimal binary search tree? Optimal binary search tree. For example, if you want to search 30, how many comparisons you require here? So 1 and 2. So 2 comparisons are required. But here it is only one comparison is required because it's a root element. But here 1, 2, 3. 3 comparisons are required for searching of 30. And here it requires only one comparison, right? So if you want to search the 30, we are having a different possibilities. Among that, these two comes under the optimal. These two comes under the optimal because it requires a minimum number of comparisons. So with one comparisons we can get the success, and here also we can, with one comparison we can get the success. For example, if you want to search for 20, so it is one comparison, it requires the 3 comparisons, it requires the 2 comparisons, it requires the 2 comparisons. So you can check. So these 3 will be the optimal. Okay, any one we can draw. Okay, so like that. So optimal means with the minimum number of comparisons, we are supposed to get the success. Okay, so less number of comparisons, the search operation should be done. Right? So that you can see, in order to search all these elements, see, I'll draw here and I'll explain you. If you consider the same three elements, some 10, 20 and 30, so I'll give you a few examples. So 20 and 10, this is the first case. If I go with the 20, I can get a 10 and I will get a 30 here, and if I get a 10 here, I will get a 20 here and I will get a 30 here. So let us take only the three possibilities. We'll be having a more number of possibilities to draw the tree. So here, how many comparisons we require? For 30 it will be 1, for 20 it will be 2, for 10 it will be 3. And here for 20 it will be 1, for 10 it will be 2, for 30 it will be 2, for 10 it will be 1, 2 and 3. So what is the average cost for search? Average cost, 1 comparison, 2 comparison, 3 comparison by 3. And here 1 plus 2 plus 2 by 3. Here 1 plus 2 plus 3 by 3. So which is nothing but, here it is a 6 by 3, it is a 5 by 3 and it is again 6 by 3. So obviously this is the optimal binary search tree for these elements among these three. Okay, there are many possibilities. We can go with the one more possibility. So let us take a 20 here, and here we can give a 30 here, and here it can be 10 here. So this is also one more possibility, and we can compare all the things. But among these three, we can say that it is a 5 by 3. The cost will be 5 by 3. That means it requires a minimum cost to search all the three elements. So this will be called as an optimal binary search tree. So which will have a minimum comparisons. So if there is no comparisons, if there is no search, obviously this will be the binary tree. No doubt at all. All the three comes under the binary trees. Now we will see how can we find out the optimal binary search tree among a different binary search trees, different combinations. Okay, so if we take some 4 elements, there will be a lot of combinations of, we can draw a lot of combinations of binary trees, binary search trees. But among that, we have to find out the optimal binary tree. So that is the problem here. How to find the optimal binary tree? That means with a minimum cost. So for this, first we have to find out the root element. So which root element will give the minimum cost of the complete tree? So here we'll be having two options. One is the keys, which are nothing but elements, and another one is probabilities, or sometimes we can also call it as a frequencies, the frequency for a successful search of an element. Okay, so we'll be having these two things. Okay, and there will be also the third thing, probability of success and probability of unsuccess or not success. So there will be two types. So we can implement this OBST with the two types. One is with the keys and probabilities of success, and another one is the keys and probability of success and probability of unsuccess. Right? So two ways we can find out the optimal binary search tree. So now we'll go with this process. That means with the keys and corresponding frequencies or the probabilities of success. Right? Yes. Now we'll see. We'll take a problem and we'll solve it. So we required keys and the probabilities or frequencies. So here my keys are 10, 20, 30 and 40. I'll take only 4 elements. Okay, 4 elements. So the corresponding keys 4, 1, 3, 2. These are the probabilities. Now we have to find out the optimal binary search tree. That means the binary search tree with a minimum number of comparisons. So we can construct a lot of binary trees. For example, I will take a 10 here, so 20 here, and 30 here, and 40 here. So this is also a binary search tree. And if you consider 30 as a root, I can go with a 20 here, and a 40 here, and here again a 10. This is also one binary search tree. And if you go with a 20 as a root, I can get 10 here, 30 here, and 40 here. This is a one more binary search tree. If you go with a 40, and you can go with a 30 here, 20 here, 10 here. So this is the one more. So like that, there will be a lot of combinations of binary search trees. Among these, we have to find out the optimal binary search tree. Now, let us consider, see, this will be using some table. We are supposed to fill the table. So first I will draw the table here. So 0, 1, 2, 3, 4. Because we are having a 4 nodes. So similarly on the rows also I will go with a 1, 2, 3, 4. So 4 rows and 4 columns. So I am constructing the table with 4 by 4 size. And now we have to fill out the cost of each and every node to other nodes. So this is the use of this table. So what is the main purpose of dynamic programming is memorization or tabulation. That means storing the results for the future purpose. So now here let us consider this as I, rows as I and columns as J. So I'll tell you what is that I and J. Now we have to consider what is the root. Okay, which should be used as a root. For example, for the first case, if there are no nodes, so we can have 0 nodes in a binary search tree, 1 node in a binary search tree, 2 nodes in a binary search tree, 3 nodes in a binary search tree, and 4 nodes in a binary search tree. Okay, yeah. So this is nothing but I minus j is equal to 0. This is, sorry, j minus I is equal to 0. Always j should be greater than I. Okay, so j minus I is equal to 1. J minus I is equal to 2. J minus I is equal to 3. J minus I is equal to 4. So that implies a tree with 0 nodes, tree with 1 node, tree with 2 nodes, tree with 3 nodes, and tree with 4 nodes. Now what we have to find? We have to find out the root. So which we have to consider it as a root. So if it is 0, 0 nodes, that means there will be no roots. So there will be no cost. So when happens in this one? So obviously whenever I becomes j, then this becomes 0. That means let it be C as a cost 1 1, cost 2 2, cost 3 3, cost 4 4. Okay, so always this becomes zeros. Okay, so I'll fill this one 0 0, 1 1, 2 2, 3 3, 4 4. All the costs are 0. Now let us consider the second one. That means j minus I is equal to 1. J minus I is equal to 1. That means if it is having only one root node, so that means I and j, you can check 0 1, C of 0 1, C of 1 2, C of 2 3, C of 3 4. So you can check I and j. So let us consider C of I, j. 1 minus 0 is 1, 2 minus 1 it is 1, 3 minus 2 is 1, 4 minus 3 is 1. You can check it. So 0, 1, okay, 1, 2, this one, 2, 3, this one, 3, 4, this one. So that means this is the next diagonal position. Next diagonal position. So that you have to find out. So what we are saying, 0, 1. 0, 1. So if it is there only one element. So always remember, you don't consider this I value. Start with I plus 1. Okay, don't consider the I value, start with the I plus 1. Now 0. So we should not consider 0. So I plus 1, 0 plus 1, 1. And the end is j, that means 1. So only one node. What's the first node? 10. So if there is 10, see the formula I am writing here, C of I j is equal to minimum of C of I k minus 1 plus C of k j plus W of I j. W is nothing but a cost, complete cost. So I'll write somewhere else this one. Okay, no problem. As of now, leave it. So C of 0, 1, that means C of 0, and here minimum, this is I less than k and less than or equal to j. That means k value will be in between greater than I and equal to j. Greater than I and equal to j. So that means, so 0 less than k less than or equal to j. So in this case, ij. So what is the value of k here? So g greater than 0. So we should not consider 0, right? Greater than 0 and 1. So here it is 1. J value is 1. So obviously the value will be k is equal to only 1. So only 1. If k value is only 1, you can see. So hope you understood this one. Now we will consider one by one. So we are now in this position. I am erasing all the remaining, okay, for calculation purpose. So we need to calculate C of 0, 1. So C of 0, 1 is equal to a minimum of, okay, so that means only one element is there. One element means only 10, the node 10. So what is the frequency for search of 10? It's a 4. So simply you can write it here 4. Okay, so if here it is a 4, 1, 2. So you should not consider 1, only 2. So that means second element 20, frequency is 1. You can replace it here 1. And 2, 3. 2, 3. So 2, 3 means don't consider 2, the third one. So third one is the 30. 30 frequency is 3. You can simply use here 3. And the next one is 2. Here it is 2. Okay, don't confuse. I'll explain you this one. So see, if it is 2 nodes, what we have to get? J minus I is equal to 2. For example, consider 10, 20, 30, 40. So what we are doing? First, this one completed. So either 10 or 20 or 30 or 40. These are all individual nodes. So that's in this diagonal. Now we have to suppose to find what is the 2 nodes. J minus I is equal to 2. So for that we can write it as C of 0, 2, C of 1, 3, C of 2, 4. So we can't go with the 3. If it is 3, then it will be 5. So there are only 4 nodes are there. So 1, 2, 2, 3 and 3, 4. So that we can go with this one. Okay, see. Now we are replacing this one. So we have to find out C of 0, 2, the cost of 1, 3 and the cost of 2, 4. For example, let us go with the 0 and 2. 0 and 2. 0 to 2. Right? So only 2 elements are there. That is 10 and 20. Only 2 elements are there, 10 and 20. So you can check the possible binary trees are 10, on the right hand side 20, and if it is 20, left hand side it is 10. Only two possibilities. So what's the this one frequency of 10? It is a 4. Frequency of 20, it is 1. Frequency of 20, it is 1. Frequency of 10, it is 4. So how many comparisons required? One comparison, and here it is two comparisons. Here it is one comparison, here it is two comparisons. Now find out the cost here. So one comparison into 4 plus two comparisons into 1. So which is nothing but 4 plus 2 is a 6. And here you can see the cost is equal to 1 into 1 comparison plus 4 into 2 comparisons is equal to 1 plus 8, which is 9. So among that, which will be the optimal? Obviously, if 10 is a root node, then it will be an optimal. If 10 is a root node, it will be an optimal, right? So with this, because we need only 6 comparisons, that means a 6 cost. Cost is 6. Here cost is 9, which is greater than 6. So this will be the optimal. So the same thing we'll be getting by using this formula. I'll write this formula here once again. So C of I comma j is equal to minimum of I less than k less than or equal to j, C of I k minus 1 plus C of k comma j plus W of I comma j, where W of I j is nothing but a weight or a cost. Okay, cost. Now you can consider the same thing here. Okay, we'll do the same thing by using formula. We have to do this thing for each and every possibility, but here it is only 2 elements, we are having only 2 combinations. If that is a 3, we'll be having a lot of combinations. If it is a 4 nodes, we'll be having a more combinations. So this is a generalized formula to find out this particular cost. For example, consider the same thing 0, 2. So C of 0 comma 2 is equal to minimum of 0 less than k less than or equal to 2. Okay, so 0 less than k less than or equal to 2. That means k will be either 1 or 2. So we have to write down 1 or 2 and we have to take out the minimum. So this is the minimum. So I'll write here C of I is 0, k minus 1. If k is 1, k minus 1 will be 0 plus C of k is 1, j is 2. So this is a I value, this is a j value. Okay, this is one possibility. Now if k is equal to 2, then it will be 0 comma k minus 1, 1 plus C of, what is here? K is 2, 2 comma 2 plus W of 0, 2. So that is the 0 of 2 means only we have to consider other than I plus 1 to j. That means I plus 1 means 1 to 2. So 1 to 2, here it is a 1, 2, 3 and 4. 1 to 2, that means 4 plus 1, it will be 5. The frequency 4 plus 1, it will be 5. So this will becomes 5. Okay. So what we have to do? Check out. Cost of 0 comma 2 is equal to minimum of, okay, first C of 0, 0. You can go with the table. 0, 0, cost 0 plus cost of 1, 2. Cost of 1 and 2 is 1. And this one, C of cost of 0 and 1. 0 and 1, it's 4. Cost of 2, 2. 2 and 2, it's a 0. Plus, what's the 5? So how much you will be getting? 1 plus 5, either 6, 4 plus 5, either 9. So what we got in this way. So these are the two different ways. Actually, based upon the frequency, if you are able to draw the tree, then it will be simple to find the cost. But if there are more number of nodes, so we have to find out for all the combinations. So that will be somewhat difficult. So that's why we can use this particular formula to find out the cost, to find out the cost. Okay, so now which one we have to consider? 6. 6 we are considering, right? So if you consider 6, what is the root node here? So here you can apply 0 to 2, it is 6. And what is the root here? So whenever the k becomes, so this is the solution, right? Whenever the k becomes 1, we are considering it as the optimal, right? See, the first 10, k is equal to 1. So this is the k value and this is the elements and this is a probability, right? So whenever the k becomes 1, this first case, if you consider first case and second case, first case only we are getting the optimal solution. So first case k is equal to 1, right? So you can represent it here as a 1 as a root node. So similarly here also you can see 4 is a 1 is a 2 as a root node, 3 as a root node, 4 as a root node. Okay, now consider the same, apply the same formula to find out the cost of 1, 3. So now I am not drawing the trees anymore. I am directly using this formula to find the cost, okay, for remaining process. So I use this place to find out the cost of everything. And see, we are just storing the information in the table so that we can retrieve the data whenever it is required in order to avoid the recalculation. Now, C of 1, 3, so is equal to a minimum of 1 less than k less than or equal to 3, and what we have to do, C of I 1, k minus 1. So here k will be becomes 2, 3 because 1 less than k less than or equal to 3. That means k will be in between greater than 1 and less than or equal to 3. So k of 1, 2 minus 1, 1 plus C of k, 2 and 3. This is one possibility. And one more possibility, whenever k becomes 3. So 1, 3 minus 1, 2 plus C of k. That means a 3, 3. Sorry. Plus W of 1, 3. So this we have to find out. Now you can find a minimum of C11, 1 cost it is 0 plus 2, 3, 2 and 3 cost is 3. So simply remember this 4, 1, 3, 2 are cost and 1, 2, 3, 4 are the root nodes. So 1 represents this 10, 2 root node means a 20 as a root node, 3 means a 30 as a root node, 2 means a 40 as a root node. So next, if there are 2 items, we have to consider 1 as a root node so that we will be getting the optimal solution. So 0 plus 3 and C 1, 2. 1 and 2, it's a 1 plus 3 and 3. 3 and 3 it is 0. Yes. Plus W of 1, 3. So I should not consider 1 here, right? So we are considering from only 2 and 3. So 2 and 3. What is the profit of 2 and 3? That is the cost of 2 and 3. 1 plus 3 is a 4. Now, what is the minimum value here? It will be 7 and it will be 5. So obviously 5 will be minimum. 5 will be minimum. Right? We have to consider 5L. So what is the value of k? That means a root node. So the second case we are considering. In the second case, what is the k value? 3. So 3. So in these two things, that means from 20 and 30, in between 20 and 30, 3 should be the root node. That means the 30 should be the root node, then only we will be getting the optimal solution. So just represent that there. So the cost is 5 and 3 is a root node. Okay, 3 is a root node. Now, see here it is a 5. Now again we have to consider C of 2, 4. One more possibility, 2 and 4. So the same thing apply here. So we have to fill all the table, right? So here always the j should be greater than I. So we'll be getting only the upper triangle. Okay, we can ignore the lower triangle. So next C of the next one is a 2 comma 4, and you can see a minimum of 2 less than k less than or equal to 4, and see the k values will be 3 and 4, which is minimum value 2, that means a greater than 2 we should consider. So C of what we have to do, I k minus 1, I is 2, k minus 1 3, plus C of 3 and no, k is 3, no, k is 3 means here 2, 3 and 4, and similarly C of I came 4, 4 minus 1 3, plus C of 4 comma 4. So what we are getting, plus W of 2 comma 4. So we have to consider the frequencies of 3 and 4, right? So 3 and 4 means these two things, which is a 5. So this will be 5, this will be 5. So we have to consider the values, the minimum of, so C2 comma 2, cost of 2 which is 0, 3 4, cost of 3 and 4, cost of 3 and 4, it is a 2. Next, cost of 2 and 3, 2 and 3, it is a 3. And 4 and 4, 4 and 4, it is a 0. Plus 2 4 means it's a 5. So among these minimum values, it will be 7 and this will be 8. So 7 will be the cost of 2 and 4. So when we are getting the cost 7, what is the root node? So first case we are considering so that we are getting the optimal, right? In the first case, what is the k value? It is a 3. Okay, so 3. Now update here. So the cost of 2 comma 4, 2 4 will be 7 and the root should be 3. The root should be 3. That's most important, because after that, after completion of this table, so we are supposed to draw the tree, construct the tree. That will be based upon these root nodes, because these are the root nodes we are using to get this particular minimum cost. Okay, yes. So there are all possibilities has been completed for 2 nodes. Now gradually increase. That means 3 nodes. So what happened to get the 3 nodes? So you need to find out the root if there are 3 nodes. Okay, so 3 nodes. What is the root if the tree is having 3 nodes? That means j minus I should be 3. J minus I should be 3. So starting from 0, if you can consider 0 comma 3 and C of 1 comma 4. So you'll be getting only 2 possibilities. If you go with the 2, then it will be automatically 5. So there are no 5 nodes, only 4 nodes. So there are only 2 possibilities here. So first let us consider C of 0 comma 3. We'll find out. So a minimum of 0 less than k less than or equal to 3. What we have to do? C of 0 comma, so here k will be becomes 1 2 3. 3 possibilities are there here. 3 possibilities. So among these 3, which one should be the root node to get the optimal solution? So k value 1 0 plus C of 1 comma 3. And similarly the second one, if k value is 2 0 comma 1 plus C of 2 comma 3. And if it is k value is 3 0 comma 2 plus C of 3 comma 3. So just go with this formula. What we have to add? W of 0 comma 3. W of 0 comma 3. So that will be minimum of, you can calculate 0 0 plus 1 3. 1 among 3. So 5. Next 0 1. 0 1 it is 4. And 2 3. Yeah. 2 3. 2 3 it is a 3. And then 0 2. 0 with 2 it is a 6 plus 3 3 it is a 0 plus, what's the weight here? So we have to consider the weight from I plus 1. That means 1 to 3. So 1, 2, 3. So 4 plus 1, 5, 5 plus 1, 5 plus 3, 8. So it will be 8. So the cost will be a minimum of, so what's the minimum value here? So 5, 7, 6. Okay, 5, 7, 6. So 5 is the minimum value, 5 plus 8, it will be 13. So we have got the cost of 0 to 3 is 13. When we got this 13? By considering the first case. What's the k value in the first case? K value in the first case is 1. So it is 13 with a 1 as a root node. 13 with a k value as 1 as a root node. Okay, now hope you understood, right? So this is the case where we'll be getting the optimal solution. So whenever the k value becomes 1, we are considering the optimal solution. So that means if in these three, 10 will be the root node, then only we'll be getting the optimal solution. Now, there is a one more possibility. There is a one more possibility to find the root node. So which is C of 1, 4. So which becomes minimum of 1 less than k less than or equal to 4. And C of, see, whenever here k becomes 1, 2, 3 and 4. Whenever k becomes 2, 1, 1 plus C of 2, 4. Similarly, C of 1, whenever k becomes 3, 1, 2 plus C of 3, 4. So because it is a k, k minus 1, kj. And see here it was also C of 1, 4 is a k, so k minus 1, 3 plus C of 4, 4. And we have to add the frequencies from 1 to 4. That means 2 to 4. So what is the values? The minimum of, what's the values here? C of 1, 1, which is a 0, plus C of 2, 4, 2, 4, it's a 7. And again 1, 2, C of 1, 2, it's a 1, plus C of 3, 4, 3 and 4, it is a 2. C of 1, 3, 1 and 3, it is a 5. Plus C of 4, 4, it's a 0. Plus this one. So now we have to consider these three. 2 to 4. 1, 3, 2. That means total 6. So among these three, which one is the minimum? This one. That means we are considering the second case. So 3 plus 6, it is a 9. Okay, 3 plus 6, it is a 9. So now what is the root node here? So second case. In the second case, what is the k value? 3. So 3 will be the root node. So 9 will be the cost. And here also I will go to with the 9. And the root node is 3. And there is a one more possibility. So now we are considering all the 4 nodes. Right? We are considering all the 4 nodes because we are having only 4 nodes. If you are having 5 nodes, then there might be 2 more possibilities. Okay. So 4 nodes. We are having only 4 nodes. We are having 4 nodes. So that means j minus I is equal to 4. That is, we will be having only one case among that. That is 0, 4. So C of 0, 4 is equal to a minimum of 0 less than k less than or equal to 4. And you can now apply C of, whenever k, here the k becomes values of 1, 2, 3 and 4. K values are 4, right? So whenever k becomes 1, then 0, 0 plus C of 1, 4. When k becomes 2, 0, 1 plus C of 2, 4. So here I k minus 1 kj. C of 0, when k is equal to 3, 2 plus C of 3, 4. And whenever k becomes 4, 0, 3 plus C of 4, 4. Plus W of 0, 4. So here what we have to do? We have to consider from I plus 1. So all these things we should be considered. Now let us calculate a minimum of, so 0 0, its a cost is 0 plus 1 4, 1 and 4, it's 9. Next 0 1, 0 1, it is a 4, 2 4, 2 with 4, it is 7. Okay, next 0 2, 0 to 2, it is a 6 plus 3 4, 3 with a 4, it's a 2. 0 3, 0 with a 3, it's a 13 plus 4 4, 4 4, it's a 0. Plus, wait, 4 plus 1 plus 3 plus 2, that means total 10. Now what will, among these things, what's the minimum value? It's a 9, it's 11, it's 8, it's 13. So this is the minimum. So 8 plus 10, which is 18. 8 plus 10, which is 18. So when we are considering this 18, the third case. In the third case, what is the key value? What is the key value in the third case? 3. So 3. So the cost is 18 and 18 and it is 3. Now you can see the root node is the third element, which is 30. Third element, which is 30. Now we have completed the construction of a table, right? Now we have to construct the tree. We have to construct the tree. How we have to construct the tree? So only one formula is there. So which is R, that is a root node. So of 0, 4, of 0, 4, or you simply can write it as I, j, which is a k. So obviously left node will be R of I, k minus 1, and here it is I, R of k, j. So the same thing we have to apply here. Now, what is the node? 0 to 4. So we have to consider all the 4 elements, right? So when we are considering all the 4 elements, what is the root node in which we are getting the optimal solution? So our problem is having 4 elements. Okay, our problem is having 4 elements. So this will be the root node. Which will be the root node? 3. So third element means 30. So here the k value is 3. So I am writing the element, okay, k value. So after that, I have to write it as here R of, what is this one? 0, k minus 1, 3 minus 1. Okay, 3 is a k. This is a k value. Okay, so 3 minus 1, 2. 0, 2. 0, 2. What is the root node? 1. So first element. Okay, just remember here these are the k values. K value means the order of elements. Okay, not the 1. 3 is not an element. 3 means third element. 1 means first element. 2 means second element. Okay, now what is this one? R of k. What is the k value here? 3. See, this is a k value. 3, j means 4. What is the 3, 4? 3 and 4. Okay. So what is the k value? 4. So this should be written here. That means the fourth element. Fourth element in this order, right? Now expand this one. We have to expand until we get the 0, 0. Okay, until 0, 0. Now again, R of, see, I value is 0, k value. So here it is a k. 1 minus 1, 0. So R of 0, 0, 0. So you can remove this one. And what about this one? R of k. See, R of k. K means 1. 1, j. J means 2. 1, 2. 1, 2. It's a second. That means a second element. Second element. Now expand this one. What is this one? R of I means 3, k minus 1. Here it is a k. 3. So which is 0. So this is not possible. Okay. And expand this one. R of, what is the k value? K value is 4. When j value is a 4, which is again 0. across. Now you can construct this tree. So third root, first element, second element, and a fourth element. Now you can consider this one. See, I'll erase this one and I'll draw. What is the third element? 30. First element on the left, 10. Second element on its right, 20. Fourth element on its right, 40. And you can check about this binary search tree. So 30 is the root. So left side we are having the less than 30 and right side we are having the greater than 30. If you consider 10, left side there are no elements, right side we are having the greater element, right? So this is the optimal binary search tree we can construct from these elements with the probability of success. So this is only having the probability of success in the search. Okay, so there is a one more possibility there. We can have a one more chance. That means the probability is for unsuccessful search. Okay, that will go with the next session. So hope you understood. Just by observing this formula, we are supposed to use this table. We have to fill this table. So you can observe we have calculated 0, 0, 0, 1, 0, 2, 0, 3, then 1, 1, 1, 2, 1, 3, and 2, 2, 2, 3, 2, 4, and all these things we have calculated to find the root element. That means this is a bottom-up approach. So this process we can call it as a tabulation. Okay, not a memorization. It's a tabulation. It's a bottom-up approach. Right? So hope you understood the optimal binary search tree. The difference between the tree, binary search tree, and the optimal binary search tree. So among these, from these elements, we'll be having a multiple of binary search trees. But among that binary search trees, we have to find out the optimal binary search tree based upon the probabilities or the frequencies given. Based upon these frequencies, this is the binary search tree which gives the less number of comparisons. Right? So hope you understood this. Yeah. So if you are having any difficulty regarding this one while practicing, so feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed my session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.